looking at the composition of a compound. So we can also break these guys, or molecular compounds, down based on the numbers of its constituent atoms. So in terms of percentages of mass of its elements, just like Dalton did way back in the day. So if we got ethanol, C2H5OH, right, that's the stuff in drinkable alcohol, right, not to be confused with wood alcohol, which will make you go blind. The mass of, we got 2 carbons, right, so we got 2 carbons at 12.01 grams per mole, so we'll have 24.02 grams of carbon in 1 mole of ethanol, right, so they're going to assume 1 mole. Right? And in that 1 mole, we'll have 24.02 grams of carbon. You'll figure out the mass of the hydrogen by doing 6 moles. Right? So you got 5 and 1, that's 6, times the molar mass, 1.08, and we'll end up with 6.046 grams of hydrogen. And I really should have left those atoms on there. And for the mass of oxygen, it'll be, in 1 mole, you'll do 16 grams per mole. Right? We only got 1 oxygen, so 16 grams. And we'll end up with a total of 46.07 grams of ethanol in 1 mole. Pro tip: the abbreviation for mole, mole in shorthand, is mole. Right? You do not write that out as just plain M. Right? As tempting as it is, and as lame as a shortcut abbreviation as that might be, right? You're saving 1 whole letter. Do not write M for mole. Right? M is something else. M, we will lowercase m, we will in chemistry call molality. Which is a separate unit, and we'll talk about that in chapter, I think, 12. All right, and so the next course in the sequence. So our mass percent, we're just going to figure out the percent of the element in 1 mole of a compound with a total mass of 1 mole of the compound by multiplying the result by 100%. So our mass percent of carbon, we just took the mass of carbon in 1 mole of C2H5OH divided by the mass of 1 mole of C2H5OH times 100. So 24.02 grams of carbon divided by 26.07 grams of ethanol times 100 means it's 52.14%. And this one isn't too bad, right? You get to make some assumptions. Like, you can assume it's 1 mole, right? Or you could assume it's 100 grams and figure it out by a 100-gram basis. A little trickier question is to kind of go the other way and figure out, well, here's some masses. How do I come up with a molecular formula? And we will talk about that when we do combustion analysis. So let's look at another example. So carvone is a substance that occurs in 2 forms, having different arrangements of the atoms, but the same molecular formula. One type of carvone gives caraway seeds their characteristic smell, and the other type is responsible for the smell of spearmint oil. And I have bought these 2 things and 2 different enantiomers. That means they're 2 different shapes, and I cannot honestly tell the difference between the 2. But we're going to compute the mass of each element in carvone. Right? So our objective. We're going to find the mass percent, right? That's where we're going to stop, of each element. Our molecular formula was made available to us as the form of C10H14O. We need, in order to find the mass percent, we're going to find the mass of each element in 1 mole, and then we're going to find the molar mass of the carvone. So determine the mass of each element in 1 mole. We got C10H14O. Right? We'll start off with our mass of carbon. We're going to do 10 times 12. 100 grams per mole, 120.1 grams. The mass of hydrogen in 1 mole would be 14, because we got 14 H's, times 1.08 gives us 14 grams. And the mass of oxygen, we only have 1, times 16 is 16 grams. Now we can just add this guy all up. pick out which one we want to figure out the mass of, right? So this is making an assumption of 1 mole. We can make other assumptions that like it's got 100 grams, right? Once you kind of figure out these relative percents, it's pretty easy to interchange between one and the other. So determine the molar mass of the C10H14O. Well, we're going to take the mass of each element, right? And you're just the molar mass of each one, multiply it by the number you got, and add them all up to get your molar mass of the complete molecule. And then you determine the mass of each element in step 3. So in step 2, we got 120 grams plus 14 plus 16 gives us 150 grams. That's going to give us our 10 carbons or 14 hydrogens and our 1 oxygen to give us the total of each kind of element in our molecule. Comes out as 150.2 grams. And I would have just done this step first, probably. And then figured it out directly from the atomic masses. Then determine the mass of each element, right? This is going to give us our denominator, basically. So for our carbon, 120.1 grams divided by our total, right? That's this guy, times 100, 79.96. Our hydrogen is going to be 9.39%. When you are doing these kinds of calculations, right, the hydrogen, right, you may have a lot of hydrogen, right? There are more hydrogen atoms in here than anything else, right? If I take my carbon and my oxygen together, there's 11 of those guys, and there's 14 hydrogens, right? But our hydrogen is really, really light, right? It's just going to be, for one hydrogen atom, 1 gram per mole, roughly. So my relative percent mass for hydrogen, even though I might have a lot of hydrogens, is often going to be the smallest component, right? And our oxygen, even though we only got 1 of them, is a pretty major component because it's heavier than all the other guys, right? So again, you're kind of looking at this like you got to weight these guys with their percentages and by their atomic mass. Right? But you're doing the same thing. You're taking your 16 grams of oxygen that you calculated before, dividing by the new total, times 100. So our formulas are determined by using a weighted sample and one of the following techniques, either decomposing it into its composite elements, all right, or by introducing oxygen to produce substances such as carbon dioxide and water, which are collected and weighed, right? So what we're going to do in this, what we call combustion analysis, right, we're going to run stuff through an analyzer that is going to burn things up, right? When you burn something up, right, your products are often carbon dioxide and water, right? So these are those are the two products of a combustion reaction, products of combustion. Right, so our two combustion products are going to be CO2 and H2O. So this is a very schematic-y version of one of these carbon analyzers. You're going to flow oxygen through, right? You got some sort of sample in here, and what's going to happen is this sample is going to catch on fire, and it's going to burn, and it's going to combust. And so you'll end up with carbon dioxide, water, those are two primary combustion products, O2, which is any excess O2, right? We're going to put in excess O2. And then other gases, right? We can put in something that absorbs water, like magnesium chlorate, right? And we're going to get a mass of water, right? Which is going to tell us our moles of water, which is going to tell us our moles of hydrogen. Right? So if we completely combusted our sample, any hydrogen we've got is going to get stopped here. Right? So we'll have like carbon and hydrogen and oxygen and maybe some nitrogen in here. Right? We go to step 1, we block out all of the hydrogen. Right? So the only thing that makes it over here, past on this side, we're going to lose our hydrogen. So the only thing that's getting through is like our carbon, oxygen, and nitrogen. Then we've got a carbon dioxide absorber, like sodium hydroxide. This is going to take out our carbon element, so we're going to have just the mass of CO2. Right? And that's going to tell us the moles of CO2, which is going to give us the moles of carbon. Right, so now we know how many moles of carbon were in our sample. Right, what gets through to the other side is just the rest, like carbon and nitrogen. And sometimes you can have things that will absorb the nitrogen and the oxygen. Right, so you put in some sample, hydrocarbons work really great. So things like octane or other compounds that are just going to be made of carbon and hydrogen. Other ones get a little trickier because then you're like, it's Gilligan's Island and the rest, and you're like, well, who are those guys? So our empirical formula is going to derive from an analysis like this. So back when I said last time that our empirical formula tells us the least amount of information, but is oftentimes the easiest to get in lab, right? This process that we just looked at for our combustion analysis will give us our ratios of carbon and hydrogen and nitrogen and oxygen, right? But they're not going to necessarily tell us how those atoms are arranged in our molecule. So our empirical formula is the simplest whole number ratio of the various types of atoms in our compound, and it can be obtained from the mass percent of elements in the compound. And that's what that combustion analysis gives us. Our molecular formula is going to vary for molecules and ions. In molecular substances, it's the formula of the constituent molecules, and it's always going to be an integer multiple of the empirical formula. Right? So if our empirical formula is CO2, right, I could have a molecular formula that could be CO2, or it could be C2O2, O4, or it could be C3O6, etc. Right? It's some multiple. For ionic substances, it is the same as the empirical formula. And so substances whose empirical and molecular formulas are different would be something like benzene, right? So benzene is going to be C6H6. Its empirical formula would just be CH, right? It doesn't tell us anything about how those guys are hooked up to each other. That's something like, whatever this guy is. That's traipsing dangerously into organic chemistry lab. I could tell you that it would be a pretty polar molecule and be really water soluble. But so if I take this guy whose formula is C6H12O6, I would reduce that down to CH2O. And I'm just multiplying that by 6. Our empirical formula determination, since the mass percentage gives us the number of grams of a particular element per 100 grams of compound, the base calculation is going to be based on 100 grams of the compound. So make that assumption. That makes your life easier. Right? You're talking about a percent. And 100 grams of compound makes sense if you're doing a percent because you got your 100 built in right there. So you determine the number of moles of each element present in the 100 grams. Kind of before we did that backwards, we assumed 1 mole. We figured out a percent. Here we're like, okay, we're starting out with some percents. We're going to assume 100 grams. We're going to figure out the number of moles. You will divide each value of the number of moles by the smallest of the values. If the resulting number is a whole number, after appropriate rounding, these numbers represent the subscripts of the elements in the empirical formula. If the numbers obtained in the previous step are not whole numbers, multiply. So you're doing some lowest common multiple, least common divisor type of stuff going on here. So all that math that you told your 6th grade teacher, like, I would never use that again, right? Time to write that apology letter and go, I am so sorry, Miss Johnson. I said I would never use lowest common multipliers again, and my chemistry professor is making me do that. Yours truly, a sad student. So here let's look at an example. We determine the empirical and molecular formulas for a compound that gives the following percentages of analysis based on mass percent. So we got 71.65% chlorine, 24.27% carbon, and 4% hydrogen. We know that the overall molar mass is going to be 98.96 grams per mole. So this is another given for us. Right? This is our determine, right? So that's where we're going to end up. Right? We've got our relative mass ratios. The first thing we're going to want to do is assume that you've got 100 grams, right? Because if you do 100 grams of sample and these are your mass percent, how many grams of carbon you got, right? 71. How many grams, or sorry, chlorine, you got 71. How many grams of carbon? 24.7. How many grams of hydrogen? 4, right? Can you go from grams of each of these things into moles of each of these things? Of course you can, right? You're going to go from grams into moles for the carbon, grams from moles into the hydrogen. Boom. Now you've got your 1, 2, 3 mole ratio that's going to go into your empirical formula. Preview. So our objective is to find the empirical molecular formulas given the compound. Right? These ratios, these mole ratios, these simple mole ratios, that's going to give you the, right, our ratio there is going to give us your empirical formula. Knowing this over here, right, this 89 multiplying your empirical formula, and this, right, that's going to give you your molecular formula. So find the empirical and molecular formulas for the given compound. You're going to need the percent of each element. You need the total molar mass of your compound, right? This guy's for your empirical formula. That dude's for your molecular formula. So to find the empirical formula, you assume 100 grams of compound, right? So determine the mass of each element in 100 grams, right? You had 100 grams, it was 71%. You got 71.65 grams of chlorine, 24.27 grams of carbon, 4.07 grams of hydrogen. Then you convert that into moles. So your 71.65 grams of chlorine, you divide by the molar mass. So 1 mole of chlorine is 35.45 grams. 3 grams of chlorine cancel out, and you're left with moles of chlorine on the end. You got 2.02 moles of chlorine. Right, do the same thing with the carbon and the hydrogen. 2 moles of carbon, 4 moles of hydrogen. If you look at this empirical formula right now, right, we would have something along the lines of C2, so Cl 2.021, carbon 2.021, hydrogen 4.04. The next thing you're going to do is you're going to divide this by whatever one is smallest. Right? It kind of happens to work out that 2 of these are the same. All right, 2.021. Right, and then you'd end up with Cl1, carbon 1, hydrogen 2. If you're a little bit off, right? So here it is 2.021 and this is 4.04. That's okay. Right? You can be a little bit off. Right? What you don't want is to be like halfway in between or a third of the way in between. Once you do that, you're going to determine the molecular formula for the compound. You're going to compare the empirical formula mass to the molar mass. So our empirical formula was 49.48 grams per mole. So that they're taking that carbon 1, chlorine 1, H2, and they're adding up the respective atomic masses. Double that for the hydrogen, right? Because you got 2 hydrogens in here. Right? If your molar mass is given as 98.96 grams per mole, you're going to look at this ratio here and say, well, how many times do I need to multiply this 49.48 to give me 98.96? Or you just take 98.96, you divide it by the 49.92, and you're going to end up with 2. So you're going to take your carbon, chlorine, H2, multiply it by 2, and it comes out as Cl2C2H4. So the substance comprises molecules of Cl2, C2H4. Once we've got this, then we can look at something like Lewis structure or Vesper, and we can start to figure out what that molecule actually looks like. When you're doing this, right, pro tip is that there are some lowest common multiples and things that you'll need to look at to figure out what these ratios are. Right, so knowing things like your 1/overs trends are going to be really useful. So, for example, if you've got carbon, and you divided everything out, and you got like a 1, and then over here you've got something like a chlorine, and this guy was 0.5, you'd know right away what to do with that, right? You're like, okay, I'm going to multiply everything by 2 to get rid of this 0.5, right? And I'll end up with like carbon 2 Cl1. Sometimes it'll be like as a third or a sixth. Those are a little bit harder to figure out. But if you're stuck, you just like take those things and start multiplying it. Like by, okay, did times 2 work? Now let's try times 3. Now let's try times 4. And you wait until they settle down into some nice, well-behaved small whole number ratio or really close to it.